I once again welcome you to the second series of our lecture on atomic structure and bonding. And in the first series, I would like to remind you what we talked about. We mainly tackled the concept of atomic structure. And in our beginning, we talked about a famous scientist known as John Dalton. John Dalton. And we said earlier chemists like John Dalton tried to reveal to us the model or the structure of an atom, of how atoms that make up matter look like. John Dalton, we said, came up with a theory that we called Dalton's atomic theory. Dalton's atomic theory. So, whereas there are many ideas in Dalton's atomic theory that are not applying to modern chemistry, chemistry about the structure of an atom as we know it currently, but John Dalton provides us with a good foundation to understand the model of an atom, to understand the composition of an atom. And just to remind you, the four main points that constitute, that make up Dalton's atomic theory, we have the following. Number one, that matter consists of tiny indivisible particles known as atoms. That was the first main idea in Dalton's atomic theory, that the tiny particles of which matter is composed are known as atoms. That is idea number one. Idea number two in Dalton's atomic theory is about the nature or the identity of atoms. The nature or identity of atoms. According to Dalton, these atoms of which matter is composed, if they belong to the same element, then they are identical. But atoms of one element always differ from atoms of other elements. So the major point to note here is that atoms of an element are always identical, but they differ from atoms of other elements. So this is identity. This is identity, that atoms of an element, are identical. We can even add here a word all, and we can say all atoms of an element, all atoms of the same element are identical. But they differ, these atoms of an element differ from those of other elements. In other words, if the element we are talking about is carbon, or the atoms that make up that element carbon are identical, and they are represented with a symbol capital C, all of them. But the atoms which make up this element carbon differ from those making up another element, sodium. So the atoms of sodium which we represent with capital N and small a, are different from those of carbon. But if we are talking about atoms of sodium, they are all identical because they belong to the same element. But they will differ from atoms of other elements. That was an important idea in Dalton's atomic theory. Another idea in Dalton's atomic theory is the idea of creation or destruction. Because John Dalton had looked at atoms as being the tiniest, the smallest particles of which matter is composed. According to him, those particles can neither be created nor destroyed. They can neither be created nor destroyed. And that is idea number 3, that atoms of an element can neither be created nor destroyed. That is an important idea, similar to the principle of conservation of energy, which we know in physics or in physical chemistry, which says that energy can neither be created nor destroyed, but changes from one form to another. That we can change, for example, light energy to heat energy, electrical energy to light energy, or electrical energy to sound energy, or electrical energy to mechanical energy. Now, that similar idea in the principle of conservation of energy that we know in physics is analogous or comparable to Dalton's idea in his atomic theory, which says that atoms of an element can neither be created nor destroyed. In other words, according to John Dalton, an atom is indivisible and indestructible. It is the smallest entity that can ever exist as far as matter is concerned, according to Dalton's atomic theory. The last idea we note from Dalton's atomic theory, as a reminder, is the rearrangement of atoms of different elements in what we call a chemical reaction to form a new substance that we call a compound. So according to John Dalton, if we have atoms of 2 or more elements coming together, these atoms will rearrange during a chemical reaction, resulting in the formation of a new substance known as a compound. So what does Dalton say? He says that atoms of different elements can combine in definite ratios, or definite proportions, forming a new substance known as a compound. Forming a new substance known as a compound. in a chemical reaction. In a chemical reaction. So this is the last idea in Dalton's atomic theory, that atoms of different elements will combine in specific or definite proportions, forming a new substance, forming a product which we call a compound during a chemical reaction. In other words, a compound is like a compound of elements. It's like a compound of elements. If we have an atom of hydrogen combining with some atoms of oxygen. Suppose we have one atom of hydrogen combining with the two atoms of oxygen. If we have one atom of hydrogen combining with the two atoms of oxygen, there is some rearrangement that takes place, leading to formation of a new product, a new substance. In this case, the new substance, the compound that will be formed, will be a molecule of water. It will be a molecule of water. So here we shall get a molecule of water. This statement here means that what has been atoms of elements in a chemical reaction, when they rearrange, the product becomes a molecule. We cannot talk of an atom of water, but here now we talk about a molecule of water. And that molecule is what we are calling a compound. That molecule is what we are calling a compound. So if we say that atoms combine in definite ratios to form a compound, the statement could be also stated as that atoms of different elements combine in definite ratios, forming molecules of compounds, this could be represented by capital H, if we are only to use the symbols, capital H plus 2, or in other words, one atom of hydrogen combines with the two atoms of oxygen, forming one molecule of water. One atom of hydrogen combines with the two atoms of oxygen, forming one molecule of water. That is an example in support of the fourth idea of Dalton's atomic theory. With these ideas in mind, we are now going to go to the next part, and that part we are going to look at today is a continuation of what we talked about in the previous lecture. In the previous lecture, we discussed the composition of an atom, the size of an atom, the mass of an atom, and we brought in new words, new concepts like isotope. We talked about atomic number. We talked about mass number. And today, I would like us to talk about we are going to look at a summary of those first 20 elements and how we can use the electronic configurations, their electronic configurations, to determine, number one, the group number of the periodic table to which the element belongs, and number two, the period number to which that element belongs. We'll also use that table of electronic configurations to determine the valence of that element. We are also going to use that same table to determine the stable oxidation state, the stable oxidation state of the element. In other words, does the element acquire chemical stability by losing 1, 2, or 3 electrons? Is it by gaining 1, 2, or 3 electrons? So we are going to determine the stable oxidation states, or the nature of the stable ions each element forms when it undergoes a chemical reaction. So let us look at this table, a summary of the first 20 elements, a summary of the first 20 elements, a summary of the first 20 elements, and their characteristics, and their characteristics. So we are going to draw a large table. And in this table, we are going to talk about each of those elements that we discussed. And then we look at the chemistry of each element, from which chemistry is determined by the electronic configuration. I want to repeat this one to everybody watching me, that the chemistry of an element is determined by its electronic configuration. I repeat, the chemistry, the chemical properties of an element, the chemical reactions that an element undergoes are a function or are determined by the electronic configuration of that element. So if we know the electronic configuration of that element, of an element, we can determine very many chemical properties of that element. We can determine the chemistry of that element. So I'm going to draw a table, and then we will explore, we will visit the chemistry of each element from the knowledge of its electronic configuration. So let me begin. So the first column here, I'm going to put the elements. The second column, I'm going to put the symbol of that element. The third column, I'm going to put the physical state of that element. In other words, is the element a gas, a solid, or a liquid? The physical state. The physical state of the element at room temperature. At room temperature. Another property we are going to look at is the nature. Is the element a metal or a non-metal? Metallic or non-metallic? Another property is atomic number. We are going to use the normal, the O-level format of writing electronic configuration, and also the advanced format of writing electronic configuration in the form of s orbitals p orbitals and d orbitals or f orbitals, SPDF notation. But we'll begin the electronic configuration with the common O-level format. So we are going to have another column for electronic configuration. Remember, I told you electronic configuration is only concerned with how the electrons are arranged in energy levels or in shells outside the nucleus. And I'm saying it is that arrangement of electrons outside the nucleus that determines the chemistry of an element, as I'm going to show you here. Another column, we are making it a table summarizing the chemistry of these elements. We are going to talk about the group number, also the period number, also the valency or the oxidation state, Now, another important property is the stable ion. We are going to write the symbol for the stable ion of that element. When the element has lost or gained electrons, which ion does it form? We call it the stable ion. And we shall simply look at the symbol of the stable ion. The symbol of the stable ion. Let us go back to the beginning of this table and we fill in the chemistry, and it will be this chemistry which will lead us to an interesting topic of the modern periodic table. And this table actually summarizes a lot that we would talk about the modern periodic table. So we are going to begin with the first element, the lightest element that we know, and which is actually the most abundant element on Earth, that is hydrogen. Hydrogen. Let us fill it. Let us fill in the chemistry of hydrogen quickly. The symbol is H for hydrogen. The physical state at room temperature, it is a gas. Is it a metal or non-metal? Being a gas at room temperature, hydrogen is a non-metal. Its atomic number is 1 because it is the lightest element or the smallest element, the element with the smallest atom in the periodic table. Electronic configuration remains 1. It remains 1. Or in the other states, the advanced state 1s1. So if you are from senior 5 up to senior 6 up to university, you have to write 1s1. But if you are senior 4, senior 3, senior 2, senior 1, you have simply to write it as 1 in a simple format. The group number for hydrogen could be group 1. It could be group 1 because hydrogen can lose the single electron in its outermost shell to form a stable H plus, ion. But hydrogen can decide to gain one electron to form also a stable hydride ion, H minus. In forming a stable H plus ion, which we also call a proton, hydrogen resembles helium. It resembles helium. In other words, H plus is simply one proton in the nucleus because the electron has been lost. So a hydrogen ion is also known as a proton. It is also known as a proton. For which reason, hydrogen could be placed in group 1 of the periodic table. However, if hydrogen acquires one electron, if it acquires one electron to fill the outermost shell, it will form a hydride ion, H minus. A hydride ion, H minus. And this is the behavior of all elements in group 7 of the periodic table. So hydrogen can have two alternative positions in the periodic table. It can be placed in group 1 because it tends to behave as the alkali metals of group 1. But it can also behave as the halogens of group 7 by acquiring a single electron to fill its outermost shell. So we can place hydrogen either in group 1, we can place it in group 1 of the periodic table or in group 7. In other words, hydrogen behaves at times as alkali metals of group 1, and at other times it can behave as halogens of group 7. So it has two alternative places in the periodic table. The period number. Now, a hydrogen belongs to what we call the short periods. The short period. Because in that short period, we have only one shell occupied by electrons. If there is only one shell occupied by electrons, for example, hydrogen atomic number 1 contains one proton and one shell. It contains one shell occupied by electrons. Because it has only one shell occupied by electrons, hydrogen is placed in period 1. This means that the period number of an element is the same as the number of shells occupied by electrons. If the number of shells occupied by electrons is 1, like the case of hydrogen and helium, even helium has two protons, but it has only one shell. Helium has only one shell outside the nucleus, which is occupied by electrons. This means that helium and hydrogen both belong to period number 1 because there is only one principal quantum shell or one energy level occupied by electrons. So we are going to place hydrogen in period 1 and helium also in period 1. For only one reason, there is only one shell occupied by electrons, occupied with electrons. The valence is valence 1. Now, the valence of an element is determined by the number of electrons that element can lose to gain stability, or the number of electrons that element gains to acquire stability. The number of electrons the element gains to form a stable octet or a stable duplet. That is the valence. So for hydrogen, it can either lose that single electron to become chemically stable, or it can gain one electron to fill its outermost shell to become like a noble gas, a stable noble gas structure. So that makes the valence of hydrogen to be 1. We can also say the oxidation state of hydrogen could be stated as positive 1. Positive 1. Stable ion, the stable ion is H plus. It is H plus. The stable ion of hydrogen is H plus. And I've already told you, we read that as a proton. Why do we read it as a proton? We read it as a proton because after the hydrogen atom has lost its single electron, it will remain with only one proton in the nucleus. So that means a hydrogen atom which has lost an electron is a proton. It is a proton. However, I have told you that hydrogen at times may gain one electron to fill its outermost shell to form a stable duplet like that one of helium, a noble gas. So in this case, hydrogen can also form what we call H minus, which we call a hydride ion, a hydride ion. So this explains the chemistry of hydrogen. So we can tell the chemistry of an element from the electronic configuration. We are able to tell the different physical and chemical properties of an element by looking at the electronic configuration of that element. Let us go to another element. And this second element is helium. Its symbol is capital H, small e. Remember, helium is a noble gas, and we said noble gases have complete or full octets or duplets, full outermost shells, and therefore they are chemically stable, they are chemically inert, they are chemically unreactive. They neither react or combine with other elements. And we are going to skip some properties of such elements because they don't undergo chemical reaction. So helium, we put there dash, atomic number 2, electronic configuration is again 2, or in the advanced form, we shall say it is 1s2. Group number, it belongs to group O. It belongs to group O. This is the group with all noble gases which are chemically inert or chemically unreactive. Period number, we say it is 1. What is the reason? Helium, a helium atom contains only one shell which is occupied with electrons. That is why we place it in period 1. The valence, we can leave the valence because helium does not combine, does not undergo chemical union or chemical reaction. So we leave the valence and we also leave the stable ion because the atom itself is already chemically stable. Which is another element is lithium. Lithium is capital L small I. That is the symbol of lithium. And I told you it is an alkali metal in group 1 of the periodic table, meaning it is a solid. By the way, most of the metals we know are solids at room temperature, apart from mercury. Mercury is the only liquid metal we know at room temperature. The rest of the metals, name them: gold, silver, sodium, potassium, calcium, magnesium, all other metals are solids at room temperature. So even lithium, being an alkali metal, is a solid at room temperature. So we said it is a metal, an alkali metal. It is having atomic number 3. Remember, when I say it has atomic number 3, it means there are 3 protons in the atomic nucleus of lithium. But the same number, that is 3 electrons, is also found outside the nucleus in shells, because in an electrically neutral atom of an element, the number of protons inside the nucleus is always equal to the number of electrons in shells or in energy levels outside the nucleus. Electron configuration O level format is written as 2 to 1. Advanced level, we write it as 1s2 to s1. In which group? It is in group 1. We prefer using Roman numerals when writing the group number. Period number, when I write 2 to 1, the first 2 electrons are in the first shell. The third electron is in the second shell. That means the period number is 2. In other words, there are 2 shells occupied with electrons in an atom of lithium. So the period number here is 2. The valence, I said, is the number of electrons in the outermost shell that an atom must lose to acquire chemical stability or to form a stable ion. And in this case, we have only 1 electron that a lithium atom must lose to acquire chemical stability, to form a stable cation. And when that single electron is lost by a lithium atom, the stable ion it forms is written as Li plus, Li with a superscript plus, a single plus, because only 1 electron has been lost from the outermost energy level. Let us move to another element, and this element is also a metal. In group, beryllium, when you're writing beryllium, write it with the double L, not a single L. Beryllium, beryllium. It's an alkaline earth metal in group 2 of the periodic table. And being a metal, this makes it a solid at room temperature. I said it is metallic. It's a metal. And I want to emphasize this, that the fundamental difference between a metal and a non-metal, the fundamental difference between a metallic element and a non-metallic element is on the way that element acquires chemical stability. By definition, metals acquire stability by losing electrons from their outermost shells to form a stable ion known as a cation. That is a metal. It acquires stability by losing electrons from its outermost energy level to form a stable ion known as a cation. Known as a cation. And in most cases, metals have between 1 to 3 electrons in their outermost shell. And because the number of electrons in the outermost shell is small, the element prefers to simply lose them in order to acquire a stable, a complete, noble gas-like electronic structure. So we are talking about metals and nonmetals. For nonmetals, by definition, they acquire stability by gaining electrons to fill their outermost energy levels. So that the outermost energy levels are like those of noble gases, which are energetically stable. In other words, nanometals have got 4 and more electrons, 4, 5, 6, or 7 electrons in the outermost energy level. And because the number of electrons in the outermost energy level is already high, it is closer to 8. It is closer to that of a noble gas. A nanometal prefers to acquire electrons to fill up the outermost energy level to form an outer electronic structure like that of a noble gas. So that is the fundamental difference between a metal and a nanometal. When a nanometal gains electrons to fill the outermost energy level, it becomes an anion. It becomes an anion. It becomes an anion with a negative charge. In other words, an anion is a negatively charged non-metallic atom or group of atoms. It carries a negative charge. An anion carries a negative charge. So let us continue a story. Beryllium is atomic number 4, meaning it has also 4 electrons in the outermost shell, which gives it electronic configuration 2 to 2, 2 to 2, or in the more advanced way, we can call it 1s2, 2s2. 1s2, 2s2. This means that we will have 2 electrons in the outermost shell. Those electrons are also known as valence electrons. So there are 2 valence electrons in an atom of beryllium. Those are the electrons in the outermost shell. Going to the group number, I told you that the group number is deduced. We can tell the group number by looking at the number of electrons in the outermost energy level. In this case, beryllium has 2 electrons in the outermost energy level, and therefore it is placed in group 2 of the periodic table. Interestingly, there are also 2 shells. There are 2 energy levels occupied with electrons in an atom of beryllium, and that places beryllium in period 2 of the periodic table. Remember, a period is a horizontal row of elements. A period is a horizontal row of elements. That is from the left side of the periodic table to the right-hand side of the periodic table. That is a period, a horizontal row of elements across a periodic table from left to right. What about a group? A group is a vertical column of elements from the top to the bottom of the periodic table. So when we say the period number, beryllium is in period 2. What is the valence? The valence, I said, is the number of electrons it loses to form a stable ion. And the valence now is valence 2 for beryllium. Or we can say the oxidation state here is +2, +2. The oxidation state for lithium, we can call it +1. So the valence and the oxidation state are synonymous, they are related. When a beryllium atom has lost 2 electrons from the outermost energy level, it forms a stable cation written as capital B, small e, and up we put a 2 plus, a 2 plus. This is called the beryllium 2 ion. Beryllium 2 ion. Going to the fifth element in this case is boron. Boron, symbol capital B. It is a solid in group 3 of the periodic table. Is boron a metal or a non-metal? We are going to put boron in between metal and non-metal, but because it has 3 electrons in the outermost energy level, we shall first put it as a metal, but it can also behave as a non-metal. It can also behave as a non-metal. Atomic number 5, electronic configuration, or level format 2 to 3, and our advanced format gives it 1s2, 2s2, and 2p1. The group number is group 3 of the periodic table. The period number, still there, we have energy level 1 and only energy level 2. That places boron in period 2. The valence, we can call it 3 or +3, and at the moment we can talk of B3 plus. Although I have told you boron at times behaves as nanometals. Another element with atomic number 6 is carbon. Carbon. Carbon is capital C symbol. It is a solid nanometal. It's a solid nanometal. There are not very many nanometals which are solids, but carbon is one of them. We know carbon, solid nanometal. We also know sulfur as a solid nanometal. We also know phosphorus as a solid nanometal. There are not very many. Most nanometals are gaseous and liquid, but carbon is one of the solid nanometals that we know. So it is a nanometal. Atomic number 6. It has 4 electrons in the outermost shell. So it is 1s2, 2s2, 2p2, 2p2. And that means it has only it has only 2 energy levels occupied by electrons. The group number is group 4. It is group 4 because there are 4 electrons in the outermost shell. The period number is period 2. Why? Because there are 2 energy levels in carbon which are occupied with electrons. The valence is 4. The valence of carbon is 4, and the stable ion for carbon is called a carbide ion. Carbide. carbide ion. Carbide. The carbide ion is C4 minus. Moving to another element which has atomic number 7. This is nitrogen. This is nitrogen. Nitrogen, capital N. Nitrogen is a gas at room temperature. We also know that this gas, known as nitrogen, makes up the largest percentage of air around us. Around 78 to 79% of the air in the atmosphere, the air around us, is nitrogen gas. So it is very abundant in air. It is the most abundant, followed by oxygen. Oxygen, with around 21%, is the second most abundant gas in air. But this nitrogen, being a gas, is a non-metal. We do not have any gaseous metal. No, we don't have any gaseous metal. Most gases are non-metals. It belongs to group 7 of the periodic table. Sorry. It belongs, nitrogen has atomic number 7, not group 7. Sorry. So it has atomic number 7, and that gives it 7 electrons outside the nucleus, which are arranged as 2 to 5, or as 1s2, 2s2, and 2p3. We are going to place nitrogen in group 5 of the periodic table because it has 5 electrons in the outermost energy level. Then the period number, we are going to give it period 2. Reason being, nitrogen has only 2 energy levels, or 2 shells, which are occupied with electrons. The valence of nitrogen, we are going to call it valence 3 because there are 5 electrons in the outermost shell of nitrogen, meaning to fill up the outermost shell, nitrogen has to acquire or to gain 3 electrons. But there are some compounds in which nitrogen shows valence 5. Valence 5. So we are going to say 3 or 5. The most stable ion of nitrogen is called N3 minus, which we read as the nitride ion. N3 minus is read as the nitride ion. The nitride ion. So you can see we are exploring the chemistry of each element on the basis of the atomic number and the electronic configuration of the element. Moving to another element, which element we call oxygen, with atomic number 8. Oxygen. Oxygen is capital O as a symbol. It is a gas. I've already told you that this is the second most abundant gas according to the percentage composition by volume of air. It is the second abundant gas in air, making up about 21% of all the volume of air around us, or the volume of air in the atmosphere. It is a non-metal. Oxygen is a non-metal. Remember, I told you a non-metal is that which acquires stability by gaining electrons to fill up the outermost shell to form a stable noble gas electronic structure. And atomic number is 8 for oxygen, making it 2 to 6, or in a more advanced way, 1s2, 2s2, 2p4, 2p4. Because the outermost energy level, n is equal to 2, contains 6 electrons. It contains 6 electrons. The group number for oxygen is 6. The group number is 6. But since there are 6 electrons in the outermost energy level of an oxygen atom, then it means an oxygen atom needs only 2 electrons. It gains only 2 electrons to fill up the outermost shell, to form an outer structure, an outer electronic structure, like that of a noble gas, which is chemically stable. And we are saying the period number is also 2 because there are only 2 shells, 2 energy levels occupied with electrons. The valence of oxygen is 2. I've given you the reason. And the stable ion. In other words, which ion does oxygen form after it has gained electrons? After it has gained 2 electrons, it will form an oxide ion. An oxide ion, which you write as capital O, 2 minus. An oxide ion. Oxide ion. Oxide ion. I'm going to go to another element, which is fluorine. Fluorine, which is in the group 7 of the periodic table, therefore we call it a halogen, has symbol F, capital F, and it is a gas. Fluorine is a gas, therefore it is a non-metal with atomic number 9, electronic configuration 2 to 7, or 1s2, 2s2, and 2p5, 2p5. We've placed it in group 7 of the periodic table, and it has 7 electrons in the outermost shell. So to determine its valence, we determine it from the number of electrons needed to fill up the outermost energy level to form an outer electronic structure like that of a noble gas. So it acquires only 1 electron. It acquires only 1 electron, and that gives it valence 1. The period number, there are 2 shells, there are 2 energy levels occupied with electrons. That gives it period number 2. Then the stable ion that fluorine forms can be written as capital F minus, capital F with a single negative charge because it has acquired only 1 electron to fill up the outermost energy level to form a noble gas like electronic structure, an outer electronic structure like that of a noble gas. And this ion F minus is known as the fluoride ion. Fluoride ion. Fluoride ion. In other words, we have looked at the chemistry of the first 9 elements. The chemistry of the first 9 elements, but we are continuing since our table is full. We are going to rub off and go to number 10, element number 10, which is known as neon, and it is a noble gas. It is a noble gas. Neon is a noble gas. So we are going to rub off and continue. Let us rub off these elements and we continue with the table because our target is to fill the first 20. The first 20. If we know that basic chemistry of the first 20 elements, it will be a good foundation for us to understand the basic chemistry of the other elements with the atomic numbers greater than 20. Mainly elements which we call the transition elements, so transition metals, and the heavy elements. The heavy elements of the periodic table. Okay, we are building our story of the chemistry for the first 20 elements of the periodic table. So another element which has got atomic number 10 is known as neon. So we stopped on number 9 and now we are going to number 10, which is neon. Neon is a gas at room temperature, but is it a metal or a non-metal? We leave that because we said to determine what a metal or a non-metal is, we depend on the number of electrons that are needed to fill the outermost shell. Either those which must be gained to form a full outer octet or duplet, or those which must be gained, or those which must be gained. So a number of electrons which must be gained or lost will determine whether it is a metal or non-metal. But for neon, which is already having a stable, a complete outer electronic structure that is energetically stable, we neither place it under metal or a non-metal. So we leave that and we go to atomic number here, which is 10. The electronic configuration in O level, in the ordinary way, we can write it as 2 to 8, but in the advanced way, we can write it like this: 1s2, 2s2, and 2p6. So if the number of electrons in the outermost energy level, n is equal to 2, is already full, in other words, it's already 8, then that element is having a complete outer octet and it is energetically stable. It is chemically stable. It neither reacts, it does not react with other elements. The group number is O. We can call it group O of the periodic table, or we can write it as group 8 with the Roman numerals. The period number is still period 2. Neon belongs to period 2 of the periodic table because it has only 2 energy levels occupied with electrons. The valence or the oxidation state, we leave that one because it does not react with other elements, being a noble gas. The stable ion, we also leave that one. It does not form any stable ion because it is already chemically stable. Element number 11 is sodium. Sodium has got symbol capital N, small a, And remember, I told you this is an alkaline metal. It is an alkaline metal. And that means the physical state of sodium at room temperature is solid. It is an alkali metal, atomic number 11. Remember the atomic number, which is the number of protons in the nucleus of that atom, is also equal to the number of electrons in energy levels outside the nucleus. So that gives sodium 11 electrons that are occupying the shells. The electronic configuration is 2 to 8 to 1. That is the electronic configuration of a sodium atom. But we can write it in a more advanced way as 1 S2 2 S2, those are so far 4 electrons that are filled, 2 P6 to P6. In other words, at this point, sodium has a structure, an electronic structure like that of neon. But since this one is 11, we add another energy level, which is 3S1. So the electronic configuration of sodium is this one. Either simple as 2 to 8 to 1 or 1s2, 2s2, 2p6, 3s1. And this places sodium in group 1 of the periodic table because the outermost energy level, which is n is equal to 3, has only 1 electron that is occupying it. There is only 1 electron occupying the outermost energy level. The period number, remember, we started with the n is equal to 1 energy level, n is equal to 2 energy level, and now n is equal to 3 energy level. There are 3 energy levels occupied with electrons in a sodium atom. That means sodium is in period 3 of the periodic table. The valence is 1, or we can say the valence of sodium is plus 1. The oxidation state is plus 1 for sodium. The stable ion, I told you, we tell the stable ion by simply looking at the number of electrons that atom has lost or gained to acquire a stable outer electronic structure like that of a noble gas. In this case, sodium loses only 1 electron, and the ion it forms will be Na+, which we call a sodium ion. A sodium ion. Those of you watching the video, we are moving to number 12, the element with atomic number 12. And this is magnesium. Remember, I grouped magnesium under alkaline earth metals of group 2 in the periodic table. And its symbol is capital M, small g. Being a metal, magnesium is a solid at room temperature. It is a solid metal at room temperature. The atomic number of magnesium is 12. The electronic configuration of magnesium in a simple way is 2 to 8 to 2, or we can state it as 1 S2, 2 S2, 2 P6, 3 S2. The period number is 3 because there are 3 energy levels in a magnesium atom, which are occupied with electrons. The group number, we can write it here, is group 2. Magnesium is in group 2 of the periodic table. The valence is 2, valence 2, or we can say the oxidation state is plus 2. So we write the oxidation state by beginning with the plus sign, plus 2, oxidation state. But when we are writing simply valence, we write 2. We don't put there plus. The stable ion, the word stable ion means, it means the nature of the ion. It forms when the element has acquired stability. So it acquires stability by losing 2 electrons. And the stable ion magnesium forms is Mg2+, which we call a magnesium ion. A magnesium ion. It is no longer a magnesium atom. Mg is magnesium atom, but Mg2+ is a magnesium ion. Let us proceed to the 13th element in the periodic table, which is aluminium. Aluminium is capital A, small l, that is the symbol. It is a solid metal at room temperature. Atomic number is 13. Electronic configuration is that 2 to 8 to 3, or we can write it as 1s2, 2s2, 2p6, 3s2. But remember, the S sub-energy level can only be filled with the 2 electrons. So we move to another energy level, which is 3p1. And that places aluminium in group 3 of the periodic table, because the outermost energy level has 3 electrons in it. The period number is still 3. Why? Because there are 3 energy levels. N is equal to 1, N is equal to 2, and N is equal to 3, which are filled or which are occupied by electrons. The difference is that we write the group number in Roman numerals, and the period number is written in the Hindu Arabic numerals. The valence is valence 3 for aluminium, or we can say it has a +3 oxidation state. Since the oxidation state is +3, then the aluminium ion is Al3+. Al3+ is read as the aluminium ion. Another element, which is number 14, is silicon. Silicon is capital S, small I, that is the symbol for silicon, and silicon, which is abundant. Silicon is abundant in the common sand, the sand we use for building. The sand silicon could also be found in clay, even in glass. That silicon is a non-metal, but a very strong non-metal with a high melting point and high boiling point. High melting point and high boiling point. So silicon is a solid non-metal. It is a solid non-metal with atomic number 14. Electronic configuration is 2 to 8 to 4, or we can state it as 1s2, 2 S2, 2p, 6, 2p6, 3s2, and 3p2. And this places silicon in group 4 of the periodic table. Reason being that there are 4 electrons in the outermost energy level in a silicon atom. Period number is 4, sorry, the period number is 3 for silicon because there are 3 energy levels that are occupied with electrons in a silicon atom. The valence is 4 for silicon, and we can write the oxidation state. We could say Si for minus or Si for plus. That means because silicon has 4 electrons, it can either lose all of them or it can gain 4 more electrons to make 8, to fill the outer electronic, the outer energy level, to fill the outer energy level, to form a full and stable outer electronic structure like that of a noble gas. Let us go to phosphorus. Phosphorus, symbol capital P. I said it is a solid non-metal. It's a solid non-metal. Atomic number 15, 2 to 8 to 5, the simple electronic configuration, which we can expand as 1s2, 2s2, 2p6, 3s2, 3p5. That means the outermost energy level of phosphorus has 5 electrons, and we place it in group 5, but there are 3 energy levels occupied with electrons, which is why we place phosphorus in period 3 of the periodic table, and we can give it valence 3 or valence 5. So phosphorus forms some compounds where it shows valence 3, and other compounds where it shows valence 5. The phosphide ion is capital P 3 minus. Capital P 3 minus is read as the phosphide ion. We don't call it a phosphorus ion. We read it as phosphide ion. Moving to the next element in the periodic table, this element is known as sulfur with the symbol capital S, and I said it is a solid non-metal with atomic number 16, which is why it also has 16 electrons outside the nucleus, which electrons are arranged, which electrons are configured as 2 to 8 to 6 in the energy levels. And this is also written, it is also written as 1s2, 2s2, 2p6, 3s2, and 3p4. In other words, the N is equal to 3. The outermost energy level contains a total of 6 electrons. 2 plus 4 is 6. Because there are 6 electrons in the outermost energy level, of a sulfur atom, we place sulfur in group 6 of the periodic table. So it is in group 6 of the periodic table. The reason is that a sulfur atom contains 6 electrons in the outermost energy level. There are 6 electrons in the outermost energy level of sulfur. Hence, it is placed in group 6 of the periodic table. But like you can see, the electronic configuration, of sulfur. Sulfur contains one energy level or one shell, another energy level n is equal to 2, and another energy level n is equal to 3. Only 3 energy levels which are occupied with electrons. And that is the reason why we place sulfur in period 3 of the periodic table. Period 3 of the periodic table. Moving on to the valence of sulfur, sulfur shows valence 2. In most compounds of sulfur, it has valence 2. In most compounds of sulfur, it has valence 2. Although sulfur can form some compounds in which it shows valence 6. Like I will show you when we are talking about chemical bonding. I'll show you that sulfur can combine, for example, with oxygen, excess oxygen. When sulfur combines with excess oxygen, it forms sulfur dioxide. When sulfur is roasted in air, when sulfur is burnt in air, it forms sulfur dioxide. And that sulfur dioxide that it forms, it behaves as an element with valence 6, or what we call the +6 oxidation state. Now, when excess oxygen, when excess air is passed over that sulfur dioxide gas, the sulfur dioxide will be converted into sulfur trioxide. It will be converted into sulfur trioxide gas, which is SO3. I repeat that when we pass excess air over sulfur dioxide, the product is known as sulfur trioxide. Sulfur trioxide, SO3. Now, the structure of that compound, sulfur trioxide, if we place sulfur in the center of the molecule, sulfur trioxide is seen to have that kind of chemical structure or molecular structure. In this molecular structure of sulfur trioxide, it is very clear that sulfur is using all the 6 electrons to bond with oxygen, because this is a sulfur atom in the center, and it has donated 1 electron and another electron to form a bond with the oxygen here. The same sulfur has donated 1 electron and another electron to form a double bond with another oxygen atom there. The same sulfur atom has donated one electron and another electron to form a double bond with the third oxygen atom. This means that in some compounds, sulfur shows a valence or a combining power of 6. In other words, it donates one electron there and the oxygen will donate to form that single bond. Sulfur again donates one electron here and the oxygen also donates 6 electrons to form a second bond. The same story. Sulfur donates one electron and oxygen donates to form that covalent bond. Sulfur will donate one electron and oxygen will donate also one to form that second covalent bond. In other words, when forming sulfur trioxide, sulfur uses all the 6 electrons in the outermost energy level to bond with the oxygen. In other words, sulfur is showing a valence of 6 in sulfur trioxide. We can also call sulfur trioxide, we can call it sulfur in brackets 6 oxide. Another name for sulfur trioxide, we can call it sulfur 6 oxide. The 6 written in brackets is the valence of sulfur or the oxidation state of sulfur in this compound of sulfur trioxide. So this is what I was explaining, that sulfur at times shows a valence of 6. A valence of 6. The most stable ion of sulfur is known as the sulfide ion, and we write it as capital S 2 minus. We read it as the sulfide. Not the sulfur ion, but sulfide ion. As we go to chlorine, chlorine is a gaseous halogen, which is a non-metal in group 7 of the periodic table, written with capital C and small l. I've said this is a gas at room temperature, but it is a non-metal. It is a non-metal with the atomic number 17, electronic configuration of 2 to 8 to 7 or 1 S2 2 S2 2 P6 3 S2 and 3 P5 because the outermost energy level of a chlorine atom, that is N is equal to 3, has got 7 electrons. That is the reason why chlorine is placed in group 7 of the periodic table. So we are going to place chlorine in group 7 of the periodic table. But there are only 3 energy levels occupied with electrons in a chlorine atom, and that means that the period number for chlorine is 3. The period number is 3. The valence of chlorine, the valence of chlorine is 1. The valence of chlorine is 1. The valence of chlorine is 1. But chlorine can form compounds with the valence 5 and even valence 7. They are there with the valence 5 and also with valence 7. So it has more than one oxidation state. The stable ion of chlorine is capital C, small l minus. This is called the chloride ion. In other words, chlorine only acquires one more electron to fill the outermost energy level in order to form a complete octet, a complete outer octet, like that of a noble gas. And the Cl minus is called the chloride ion. The chloride ion. Thank you, those of you who are online watching this video, and we are continuing to build the chemistry of the first 20 elements of the periodic table on the basis of their atomic numbers and electronic configuration. I am still emphasizing the fact that the chemistry of an element is determined by the number of electrons it has and the electronic configuration. Those will be the main determinants of the chemical properties of an element. Going to number 18, number 18 is neon. Number 18, not neon, I'm sorry. Number 18 is argon. Argon is a noble gas with the symbol capital A, small r. I said this is a gas at room temperature. We don't put there the metallic or non-metallic nature, but when we come to the atomic number, we put there 18. The atomic number is 18, and that means we are going to write the electronic configuration in a simple way as 2, 2, 8 to 8. When you add those, you get 18, and that is how they are arranged in energy levels. But we can write it as 1s2, 2s2, 2p6, 3s2, and 3p6, meaning that argon is the last element, with the argon is the last element with the 3 energy levels. The last element with 3 energy levels. The group number for argon is group 8, but we write it with the Roman numerals. Group 8, also known as group O. We can also call it group O, capital O. The period number for argon, remember I've said argon is the last element with the 3 energy levels occupied with electrons. And that means the period number for argon is 3. Why? Because the period number is the number of energy levels or the number of shells occupied with electrons in the atom of the element. Going to the valence, let us talk about the valence. The valence or the oxidation state, we leave it for argon. Why? Because it's already chemically stable, chemically inert, and it does not undergo chemical union. It does not react with other elements. So we don't talk about the valence, because the valence means the combining power of an element. The combining power of an element or a radical or a group of atoms known as a radical. The stable, the most stable ion formed by argon, we leave that one because it does not undergo chemical union. The second last element that we are looking at is potassium. The second last element is potassium. Potassium. Potassium, I told you potassium is an alkali metal in group 1. It is placed in the same group with the lithium, whose atomic number is 3, and sodium, whose atomic number is 11. They are in the same group and they possess the same or similar chemical properties. They are called alkali metals. Symbol for potassium is capital K. Is it a solid, a liquid, or gas? Potassium is a solid metal at room temperature. It is a solid metal. Atomic number for potassium is 19. Electronic configuration is 2 to 8 to 8. Remember, when we reach 8, it means that energy level is full and we move on. We fill the electrons in the next energy level. So we go to 1, 2 to 8 to 8 to 1. And we do the same when we are using the SPDF way of writing electronic configuration. So we shall say 1s2, 2s2, 2p6, 3s2, 3p6. Those are so far 18, like that one of argon. But this one is now the outer electronic structure is now complete. It is a full octet and stable. So we don't fill any further. We move to another energy level, which is 4s1. 4s1. This places potassium in group 1 because there is only one electron in the outermost energy level. Level 4, energy level 4 has only one electron, and this places potassium in group 1. It places it in group 1. Group 1. Then the period number is period 4. Period number 4. Why is potassium in period number 4? Because the period number is the number of energy levels occupied with electrons in the atom of that element. So potassium is in period 4. The valence is 1, which we also call the +1 oxidation state. The +1 oxidation state. In other words, in most compounds of potassium has a combining power of 1. For example, 1 atom of potassium can combine with 1 atom of chlorine to form potassium chloride. 1 atom of potassium can combine with 1 atom of bromine to form potassium bromide. The combining power of potassium is 1. The oxidation state of potassium is +1. And the stable ion of potassium, most compounds of potassium show K+, the potassium ion, as the most stable ion for most of its compounds. The last metal, or the last element, which we call an alkaline earth metals. I want you to remember that alkaline earth metals like calcium, beryllium, and magnesium are placed in group 2 of the periodic table because they have 2 electrons in their outermost energy levels. In other words, all group 2 elements, all alkaline earth metals show a +2 oxidation state, a valence 2 in most of their compounds. So the last element in our discussion is calcium. And looking at the chemistry of calcium, calcium is a symbol capital C, small a. It is a solid. It is an alkaline earth metal. It has atomic number 20. Electronic configuration shows 4 energy levels. The electronic configuration shows 4 energy levels, with the first energy level having 2 electrons, the second energy level 8 electrons, the third energy level 8 electrons, and the fourth energy level 2 electrons, coming to a total of 20, which is the atomic number. And we can write this in a more advanced electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6, and now we move to the fourth energy level, 4s2. Because the outermost energy level has only 2 electrons, that places calcium in group 2 of the periodic table. That places calcium in group 2 of the periodic table. And since we have 1, 2, 3, and 4 energy levels occupied with electrons in a calcium atom, then the period number is period 4. The period number is the number of energy levels occupied with electrons. The valence of calcium. Calcium forms compounds with mainly a valence of 2. Most calcium compounds are in a +2 oxidation state. A +2 oxidation state. And that means that for a calcium atom to acquire chemical stability, it must lose 2 electrons from its outermost energy level, forming a complete or a full outer electronic structure like that of a noble gas. And that gives calcium a stable ion of Ca2+, which we call a calcium ion. A calcium ion. Ladies and gentlemen, I just wanted to use this video to demonstrate to you that knowledge of the atomic number and electronic configuration of an element can give us more details of the chemistry of that element. I wish to stop here and wish you very nice watching and very nice and successful learning as we build for the future. My name is John Bukenya, lecturing in Makerere University and the program coordinator of Bachelor of Science External Degree Program in Makerere University Institute of Open, Distance, and E-Learning. Thank you very much. God bless you.